All right, so the recording has started. Again, thanks for joining over Zoom. As all of you know, as per the announcement last week, I'm traveling this week. So all the three classes today, Wednesday, and Friday will be over Zoom. However, I'll be posting the recordings as I do in general for all the other classes. Now, this week, we are going to look at a few more example problems, which some of them would be the solutions of your homework too. And we'll also discuss some of these example problems or similar problems to homework 3, and then summarize the non-ideal op-amps today. And then if time permits, we'll also get started with a little bit of introduction on diodes, which will continue throughout this week. So our plan would be to complete the discussions on diodes by the end of Friday. All right. The other thing is that your exam number 1 that has been posted, and the due date would be September 29th. So that's next Monday, 11:59 p.m. Now this is a take-home exam. It's going to be exactly similar to your homework assignment. So if you go to your assignments tab, you'll already see your exam 1 is already posted over there. So just submit it like any other assignment. I'll probably show some of the questions that we have for the homework 1 as well. So it's a 100-mark exam, or your exam 1 basically, or it's a 100-mark exam, and there are 4 questions over here, and the due date is September 29th. The first question is a very simple gain calculation. So if you have a input current source over here, and if your output is a voltage, then you're trying to find out the gain of the output quantity over input quantity. So basically output voltage over input current. So this is eventually a trans impedance gain that you're interested in, because you're interested in a voltage over current quantity. So please find that out. What would be the gain for the following passive circuit? Of course, the gain will be less than 1 because it's a passive circuit. The second question deals with a very similar circuit as your question number 1, but um, there is a op-amp based circuit connected within the components that you had in the previous circuit. So that would change some of the considerations that you should have for the while you are solving this kind of a problem. So please go through that and try to figure out what would be the effect of introducing this op-amp based circuitry for your question number 2. Now, question number 3 and question number 4, they are ideal op amps and non-ideal op amps. For question number 3, you are asked to find out the A infinity, or basically assuming that the op amp is infinity ideal, which means it has infinite gain, infinite input impedance, and zero output impedance. Assuming those conditions, you need to find out what is the A infinity gain, that is output voltage over input voltage, for the ideal op amp. And also you need to find out R in and R out for this circuit. So what is the R in for the entire system, looking at these two terminals as indicated? So basically you're looking into the input resistance between this terminal and this terminal. Similarly, you're looking at the output resistance between this output terminal and the ground. So that's what you're required to find out for this particular question. Now, one thing that is interesting and something that you should pay attention to is that in this circuit, as you see over here, that there are two input voltages. So there is a Vs over 2 connected, eventually connected to the non-inverting terminal of the op amp, and there's another Vs over 2 eventually connected to the inverting terminal of the op amp, right? So instead of having only one input, now you have two inputs in this particular question. And how to take care of such scenarios? You already learned something called superposition theorem, that um, if you have a linear circuit and you can apply if you can apply the theory of superposition to it, what you can do is that you can consider each of these voltage sources at a time. So you just consider the first voltage source, find out what is going to be the output, then consider the second voltage source, find out what is going to be the output, then have both of the voltage sources at the input at the same time and find out what is going to be the output voltage in that case, which is just going to be a combination of the output voltages that you had in the first two scenarios. So use your theory of superposition, and that should give you the final answer for question number 3. But for all of these calculations, assume that your op amp is an ideal op amp. Now, the next question is about non-ideal op amps. Now, Instead of assuming that the op-amp is ideal, you can assume your RIN is, let's say, 1 mega ohm, Rout is 500 ohms. The gain of the op-amp is 10,000 instead of infinity. And the open loop, um, or, or basically A naught times F open loop, that is 5 megahertz. That's the open loop gain bandwidth product. So you're multiplying your gain with your bandwidth, and that is 5 megahertz. So those are the information that is given in the question. With that, you need to find out what is the beta, that's a feedback path gain, and what is the closed loop low frequency gain, ACL, which is A infinity divided by 1 plus 1 over A naught beta, right? And as well as the closed loop bandwidth. Okay. So your question number 4 is related to non-ideal op-amps, whereas your question number 3 is completely related to ideal op-amps. Any questions on the exam 1? If not, let's take a look at a few more example problems. So we'll first take a look at the homework 2 solutions, which is also something I have already posted on Canvas. So please go through them. Homework 2 and solutions, as well as the sample questions similar to homework 3, they will help you to answer some of these exam 1 questions as well. Now, in homework 2, for each of the circuits, you are asked to find out A infinity, R in, R out, assuming that the op-amp is ideal. So A, B, and C, all of them assumed the op-amp is ideal. And then you had part D, for which you wanted to find out the loop gain for each of these circuits, assuming that the op-amp's gain is 500, and then you have R in of 100 kilo ohm, R out of 1 kilo ohm. So with that, if you take a look at the first question, that basically considers applying your input to the inverting terminal of the op-amp with a feedback going back to the inverting terminal as well. So because you have a negative feedback going back to the inverting terminal, you can apply the virtual ground property. And using the virtual ground property and using the nodal analysis method, or by using KCL and KVL, as you have learned in 3111, you can find out what is going to be A infinity. That is, if this is an ideal op-amp, what's going to be your gain for the entire system. And because this is configured in a way that the input voltage is applied to the inverting terminal of the op-amp, you already know this is an inverting amplifier. And you also know what is the gain of the inverting amplifier. That's going to be minus of R2 divided by R1. Again, that's just the formula I'm quoting, but in part A, you are actually trying to find out A infinity, which will be exactly same as minus R2 over R1. And for that, you can use, let's say, nodal analysis or KCL and KVL based analysis that you have already learned in your earlier classes. And you'll end up with A infinity to be equal to minus 4. That is minus of 600 kilo ohm divided by 150 kilo ohm. So that's pretty easy. Now, if you want to find out the input impedance, what you're going to do is that you'll get rid of any kind of independent voltage or current sources at first, of course. So basically at the input, instead of connecting this VS, you'll get rid of the VS first, and then you'll connect a test voltage source or a test current source. Now, if it is a test voltage source, the setup will look very similar to this. It will not change. It's just that instead of the source voltage, you'll just have a test voltage connected at the input. And you'll try to figure out, or we'll try to measure what is the test current coming out of this test voltage source. Now, for that, remember that this is eventually, even though you're trying to find out input and output resistances as the Thevenin equivalent resistance at the input or the output side, your op-amp or the existence of the op-amp actually affects the or actually forces some of the points to have a particular amount of voltage. Because in this case, as just as an example, you already know that because there cannot be any current going into the op-amp, so this current going into the non-inverting terminal of the op-amp is going to be 0. If the current is 0, the voltage drop across R3 resistance is going to be 0 from Ohm's law. So if the bottom terminal of R3 is 0, the top terminal of R3 is also going to be 0. And because it's a negative feedback, you have the virtual ground property for the op-amp. For the inverting terminal as well, you have a 0 voltage here, 0 AC voltage. So basically that is forcing the inverting and non-inverting terminals of the op-amps to be at 0 volt. Right? It does not mean that there is an actual ground over there. So if there is an actual ground, so let me just clear this for a moment. If there is an actual ground over here, the current coming out of this test voltage source in the input side, that current will go through the 150 kilo ohm resistor and actually go to the virtual ground, right? That does not happen because this is not a not an actual ground, this is a virtual ground. So virtual ground cannot take in any current. But what virtual ground does is that it forces the voltage of that point to zero. The voltage at this point is zero, but current does not flow in there because that's not an actual ground. It's virtually a ground. But as soon as you force your voltage to zero, and you know that the voltage on the left side of the R1 resistance is also forced to something, let's say test voltage source VT, right? So the left side is forced to VT, the right side is forced to zero, and the resistance of value is 150 kilo ohm. So all of that just forces your current, right? Your current is forced to be VT over R1. It cannot be anything else because of Ohm's law, because the left side of the resistance R1 is VT, the right side of the resistance R1 is forced to 0 volt because of the virtual ground property. And because of that forcing, the current is forced to be VT over R1. So that's basically the current I flowing through the R1 resistance. Now, if that is true, the I flowing through, or the current flowing through this R1 resistance, the current flowing through this R1 resistance, and the voltage on the left side of that R1 resistance, the ratio of those two will be the resistance seen at the input side, according to Ohm's law once again, because voltage divided by current is your resistance. So VT over I is going to be VT divided by VT over R1. So your Rin is actually going to be R1. So what the resistance that you see looking into this particular port is going to be exactly equal to R1. Okay. And that happens because the virtual ground property forces this point's voltage to be zero, even though this is not an actual ground. And because this is not an actual ground, the current actually flows in this path, right, which you have already assumed during your party. So there's no disconnect between the fact that there is a virtual ground versus the fact that all current goes through R2. Okay, so that's about R in. R out is relatively easier because you're looking at the R out in the looking into the output terminal of the op amp. So that basically makes sure that the current, or basically if you put a test voltage source over here, let's say you just put a test voltage source in this case. Of course, before that you have to get rid of all the independent voltage and current sources. That means this point will be connected to ground. But if you connect a test voltage source at the output side and look into how much current goes here, you'll see that all the current, because there is a zero resistance, this is an ideal op amp, there is a zero resistance path to ground. So you have a ground, but connected to the ground, there is a zero resistance. So an infinite amount of current flows through that zero resistance path to ground. Because there is an infinite amount of current coming out of the voltage source over here, any finite voltage source divided by infinite amount of current, that will give you zero resistance at the output. So your R out is going to be zero, and which will be the case if you have an ideal op amp, and then if the point that you're looking into is basically the output of the op amp. So that is always going to be zero, because there's always going to be this infinite current, zero resistance path through the output of the op amp going back to ground. Now, the final task that you were asked to find out is basically the loop gain. And the loop gain is something that you already know how to find out. You can you can start from the output of the dependent voltage source, or as it has been shown over here, that you first break the loop, because again, from the definition of the loop gain, you know that you first have to break the loop and then multiply all the gains that are present in the circuit. So what are the gains that are present in the circuit? You have a feed-forward path gain from the amplifier, and then you have a feedback path gain beta. The multiplication of A with beta will give you the loop gain. And for the loop gain to make sure that you understand what is the loop gain, you can break that loop. You can put a test voltage source over here at the same point where your output of the dependent voltage source was connected. You may want to draw that, or even if you don't draw that, it's fine. It's the same concept anyway. But if you just go by the book, when you are trying to find out loop gain, you first break the loop and then multiply what are the individual gains that are present in the loop, or that were present in the original loop. So in that case, you encounter basically the output resistance of the op amp. Output resistance of the op amp was given to be some value in the question. And then you traverse your way back toward the input side until the point you eventually find out what is the factor, or what is the portion of the voltage, this voltage VT, what is the factor, or what is the portion of this test voltage source VT is available back at the input side between the negative and positive terminals of the op-amp. So basically between these two terminals, right? That's what you're trying to find out. And again, I'll not go through the math over here. Maybe I'll show that in one final example, but in general, that's the concept. And you can already find out, you already know how to find voltage divisions if you have a resistive network. And we have also seen some of these examples earlier in the class. Eventually, you end up with a voltage division ratio like this. So this is going to be your beta. So go through the solution if that is not clear. But your beta is just going to be a resistive divider network, and multiply that with your original gain AV of the op-amp, which was 500. You get the loop gain. Total loop gain is gain of the feed-forward path, that is the op-amp's gain, multiplied with the feedback path's gain, that is the beta. So overall loop gain is, let's say, 37 in this particular example. Any questions here? Now, to find out the closed loop location of the pole, this is not graded in your homework number 2. So it's fine if you have not submitted it. But for your homework number 3 and for the 4th question in your exam 1, this is important. So how to find out the closed loop pole, or what is the closed loop pole, first of all? So you already know the open loop gain of the op-amp as a function of frequency can be written as this. This is what we have been seeing for the last few lectures. The open loop gain of the op-amp can be written as this because the op-amp has a low pass response. Why does the op-amp has a low pass response? Because at the output of the op-amp, if it is an non-ideal op-amp, you have a output resistance. So basically, the inside triangle, if that is the ideal op-amp, you have a output resistance associated or in addition to the ideal op-amp, and that makes your real op-amp. So you have a resistance. And then, of course, for any circuit, at any point, you'll have a capacitance to ground. So that's just the nature of circuits, that you always have a parasitic capacitance to ground at any point. Now, this RC network, if you have a resistance in series and then a capacitance in parallel to ground, this RC network is a low-pass filter. And that's why the basic way the low-pass filter's transfer function is written, you see that the transfer function of the open loop gain of the real op-amp with a finite bandwidth is written in the same way. Where A is your low frequency gain or zero frequency gain. Sometimes in books, you'll see it's written as A naught. That just means it's A at zero frequency. Your open loop pole in this particular equation, the location of your open loop pole is omega naught, that is, or omega naught or omega 1 or omega p, however way you might want to write it. Everything is fine. But that is equal to 2 pi times the linear frequency of the pole. Let's say that is f1. So 2 pi times f1 is basically your omega of the pole. Now you already know that your feedback reduces by the gain by a factor of 1 plus AB, right? Or 1 plus A beta. You already know that if your open loop gain is A, your closed loop gain becomes A divided by 1 plus A beta. Again, in feedback, we learned that. Now, your loop gain is T, which is A times beta. Now, if your A is a function of frequency, and then you're writing A as a function of S or as a function of frequency, then your T or your loop gain also becomes a function of frequency, because T is nothing but A times beta. If A is a function of frequency, T will be a function of frequency. So you can write your closed loop gain, which is A divided by 1 plus A beta. So you can write that as A divided by, or A as a function of frequency divided by 1 plus A as a function of frequency times beta. That is nothing but T as a function of frequency, because T is equal to A times beta. Now here, dividing the numerator and denominator with 1 plus S over omega naught. So you divide the numerator and denominator with that, you get this equation. Or basically, rather, okay, let me clarify that better. So basically your A, or as a function of frequency, your gain is A divided by 1 plus S over omega naught. And again, T as a function of frequency is A divided by 1 plus S over omega naught multiplied with beta. So that's what you have just by replacing A as a function of frequency and T as a function of frequency. Now, if you multiply this by 1 plus s over omega naught at the numerator and also multiply by 1 plus s over omega naught at the denominator. Then you get this closed loop equation as a divided by 1 plus s over omega naught, because you had multiplied this 1 with 1 plus s over omega naught, and that's how we ended up with this, plus a times beta, because a times beta was already there, and that was divided by 1 plus s over omega naught. Now you multiply that by 1 plus s over omega naught. So you can write your closed loop gain equation as a divided by 1 plus s over omega naught plus a beta. Now what you can do is that you can divide your numerator and denominator both with 1 plus a beta. Okay. So divide your numerator with 1 plus a beta, divide your denominator with 1 plus a beta. And in your denominator, you already had this 1 plus a beta component. Right? So this was your 1 plus a beta component. Dividing that by 1 plus a beta gives you this 1. Plus you have s divided by 1 plus a beta times omega naught. Right? So that's basically just this quantity divided by 1 plus a beta. All right. So now, as you see, very interestingly, your closed loop gain as a function of frequency also looks like the format is very similar to the open loop gain as a function of frequency as well. The open loop gain as a function of frequency looked like a divided by 1 plus s over omega naught, where omega naught was your pole frequency. The closed loop gain, the equation for that is a divided by 1 plus a beta in the numerator. And you know that that is the closed loop gain at zero frequency. So this is the closed loop gain at zero frequency, a divided by 1 plus a beta. The denominator is in the same format as before. The denominator, for the open loop gain, it was written as a divided by 1 plus s over, let's say, the pole frequency. And pole frequency, let's say, in this case was, let's say it's written by as omega naught. So it's in the same format. As you see this equation over here, it's exactly in the same format. In the numerator, you have the zero frequency gain. Now, this was open loop condition. So this was, let me put a box around this. And this is basically open loop condition. And the box here is basically what you have in the closed loop condition. So in your closed loop, you have the closed loop zero frequency gain in the numerator. In the denominator, you have 1 plus s divided by 1 plus a beta times omega naught. So interestingly, you see what has happened is that your gain has reduced by a factor of 1 plus a beta, but your bandwidth, which was omega naught earlier, has now increased by a factor of 1 plus a beta, the same factor. And this is something we already established in the class, that your gain bandwidth product remains constant. So if your gain reduces by a factor of 10, your bandwidth increases by a factor of 10 and vice versa. So if your gain reduces by a factor of 1 plus a beta, your bandwidth increases by a factor of 1 plus a beta. Now, if that is the case, you can find out the bandwidth okay, let me clear this. So for this particular question, you already found that your loop gain T is equal to 37. Your open loop bandwidth was 1 kilohertz. And if your T is equal to 37, which is 1 plus a beta, your open loop bandwidth was 1 kilohertz. Your closed loop bandwidth will increase by a factor of 1 plus a beta, which is 1 plus 37. So your closed loop bandwidth will become 38 kilohertz. Okay. So basically, you'll see that your open loop bandwidth increases by 38 times and your open loop gain reduces by 38 times, because A was equal to 500. A was equal to 500. And the beta factor that has to be equal to 1 over 38. Or very close to that, if you have some amount of approximation. Question number 2 was very similar. Again, a voltage amplifier. Again, the exact same method that we had used for question number 1. In this case, the only difference is that your input is applied eventually to the non-inverting terminal of the op-amp, whereas you have a feedback back to the inverting terminal of the op-amp. So you still have the negative feedback. So you can still apply the virtual ground property, and you already know how to solve for A infinity using the virtual ground property. So your A infinity in this case will be 1 plus R2 over R1, just from the theory or that you had learned in 3111. So 1 plus R2 over R1 That's going to be 1 plus 120 over 15. That is 1 plus 8, which is equal to 9. And in this case, remember that the voltage gain will be plus 9 volt over volt. Why plus 9? And in the previous case, it was minus 4. That meant in the previous case, because it was an inverting op amp, your phase at the output was 180 degrees shifted as compared to the phase at the input. In this case, the phases are equal, and that's why your gain is a positive gain. And that just from the name also, you will understand that this is a non-inverting op amp, whereas the previous one was an inverting op amp. Now, in a similar manner, you can find out what is going to be your R in, what is going to be your R out. In this case, because you're looking at this terminal over here, that is the bottom terminal of R3, and that's why you're trying to find out R in. You already know there is no current that can go into the op amp. So your current is 0. So your R in current is 0, and that's the reason why your R in is infinitely large. On the other hand, R out is at this particular terminal, right? Because that's the terminal where your VO is connected. You know that there is a resistive path going here, and then there is going to be some, even though there is no current that goes into the op amp, there is current that is going into the ground. There is also a resistive path over here that goes to the ground. But you have a zero resistance path from this same point through the output of the op amp to ground. And if there is a zero resistance path, all the current will actually just go through the zero resistance path. So there would be no current going through the R1 and R2 resistances. There will be no current going through the RL resistance as well. So the fact that this RL resistance is connected has absolutely no effect. The RL resistance has absolutely no effect when you're trying to find out R out, because no current goes through it if this is an ideal op amp. So all the current goes through the op amp itself, and that's the reason why your R out is equal to 0. In a similar manner as you did for question number 1, you can find out beta, and your loop gain is going to be T, which is A times beta. In this case, 500 multiplied with all these factors, the raised to divisions. Eventually, you will come up with a T of 19.3. What would be your FCL, the closed loop bandwidth? The closed loop bandwidth will be 1 plus T times the open loop bandwidth. So 1 plus 19.3 times open loop bandwidth, which was 1 kilohertz. So you get 20.3 kilohertz. Question number 3 was a little bit more interesting, because in this case, you had a current amplifier. Your input is a current source IS. The output is a current IO, okay, I out. So you're interested in finding out what is IO over IS as your current gain. So A infinity is IO divided by IS. Now again, you can, the A infinity part should be very easy, because your currents going into the op amp is 0. You know that, for example, this IO current, whatever IO current is there, that gets divided into 2 parts. One flows through 5K resistance. The other one flows to this 30K resistance. It comes here. It cannot go through the op amp, the input of the op amp, so it has to go to this path. Right? So what factor of IO is IS? That's what you need to find out. So that's basically this very simple current division between R2 and R3. IR2 is going to be I naught times R3 divided by R3 plus R2. And remember, for current division, the current going through a resistance will be directly proportional to the value of the other resistance. If there are 2 resistors, if you're trying to find out the resistive, the division of current between 2 resistors, the current through the R2 resistance will be directly proportional to the other resistance, which is R3. So IR2 is equal to I naught times R3 divided by R3 plus R2. And IR2 is exactly equal to IS, because whatever flows through R2, that has to be IS, because there cannot be any current flowing into the op amp. So that's not possible. So your IS is equal to IR2, and IR2 equal to I naught times this raised to division. So you can find out what is I naught over IS, and that's going to be 7 in this case. Now your Rin was looking at this input terminal. So how to find this out? Again, because of virtual ground property, your inverting terminal as well as non-inverting terminal that are forced to 0 volt. So this point is forced to 0 volts AC. This point is also forced to 0 volt AC. What that means is that if you have a current source at the input, let's say a test current source at the input. So instead of IS, let's just connect a test current source at the input. You know that this point's voltage is forced to 0. If the voltage is forced to 0 for any finite value of current, the resistance has to be 0. Because finite current multiplied with resistance, which is 0. The finite current multiplied with 0 resistance gives you 0 voltage. Because the voltage is 0, the resistance at the input has to be 0 for any finite current. So Rin is equal to 0. And which is good for any current amplifier because it has to be the dual of the voltage amplifier. For voltage amplifiers, Rin needs to be, or it is preferred that Rin is infinitely large and Rout is 0. For current amplifiers, it is exactly the opposite. Rin is preferred to be 0 and Rout is preferred to be infinitely large. Now, if you want to find out Rout in this case, which is between these two terminals, let's say this and this, if you want to find out Rout with these two terminals, again, let me show the calculation. This is the same calculation I showed in the last lecture as well. So you connect, let's say, for example, the test voltage source over here, and you try to find out how much is the current coming out of the test voltage source. The ratio of those two will basically be your output resistance. Now, because of the virtual ground property, remember that this point is forced to 0, which means this point is also forced to 0 because of the virtual ground property. And because there cannot be any current flowing into the op-amp's input, so there cannot be any current flowing through this, then by Ohm's law, this point's voltage is also 0 because there is no current flow through this R2 resistance. If there is no current flow, the voltage drop across R2 is going to be 0. So right side of R2 is also going to be 0. If that is 0, then the voltage or then the current flowing through the R3 resistance is also 0 because this point is also 0. Now, the current coming out of your test voltage source in that case is going to be 0 because there's no current going into the op-amp. There's also no current going to ground over here. That's what we just figured out. So if there is 0 current coming out of your test voltage source, the voltage over 0 current, that ratio is your output resistance. So voltage over 0 is infinite. So your output resistance is infinite. And you can find out the beta and the loop gain as well as the frequency response in the same manner as you did for the other questions. All right. Now let's also quickly discuss some of these questions which are very similar to your homework 3 problem. The first question is very simple. Find out A infinity, beta, T naught, and FCL. That's the closed loop bandwidth for this particular scenario. And what is this scenario? That you are applying your input voltage to the positive terminal of the op-amp. And then you have a negative feedback for the op-amp. That means the virtual ground property holds true. And you already solved this kind of a problem in your homework number 2. So that's going to be very easy. Now this is with a current input, and with the current input voltage output, you can again, I hope that with everything that we have gone through or looked into in the class, we should be able to find out what is your A infinity, beta, T naught, and FCL for this circuit as well. The solutions are actually given, so please go through the solution. I'll not go through the like them step by step, but let me know if there are any questions. So all these solutions are provided in this particular PDF, which is uploaded on your Canvas. Let me show it once again. So if you go to your Canvas page, along with homework 3, I have also posted these similar problems as example and exercises. So please go through that before solving your homework number 3. So those are the first 2 questions, part A and part B. Question number 2 is a little interesting. So for example, here you see a lot more resistances and capacitances connected over here. Why these resistances and capacitances are there? Again, if you think about it, that any voltage source Vs will have a non-ideal series resistance. So let's say now we are trying to make our circuits more and more realistic, but more realistic circuit means more complex circuits. So that's why you, in this case, you have a RS resistance connected in series with your voltage source. You have something interesting over here. Let's say you have this RB1 and RB2 directly connected to the positive terminal of the op-amp. What is this RB1 and RB2 are doing? They are, in fact, creating the bias voltage required for this op-amp. So you already learned from your voltage transfer characteristics is that if you plot your input voltage on your x-axis, and if you plot your output voltage on the y-axis, your voltage transfer characteristics looks something like this. And to have maximum amount of gain, you want to be in the middle of this voltage transfer characteristic. So you do not want to be at 0 DC voltage, because 0 DC voltage is here, right? The point 0 in your 0, 0. So input voltage is 0, output voltage is 0, or output voltage is maximum in this case. So 0, let's say V max. That point is over here. So you don't want to be at that point, because the gain at that point is flat. The gain is equal to 0. And if the gain is equal to 0, you don't want your op amp to behave in that way. If you want gain out of your op amp, you have to bias it at a non-zero DC point first, and then apply the AC signal around it. So what RB1 and RB2 is doing is applying that non-zero DC point. So you have a VCC of, let's say, 10 volt. And then if you have RB1 equal to 1 mega ohm, RB2 equal to 1 mega ohm, the midpoint of those two resistors are going to be half of your VCC. So that is going to be 5 volts. Why is it going to be 5 volts? Because think about it, the current only flows from top to bottom. Current cannot go on the right side because it sees the input of the op amp. Current cannot go on the left side because it sees a capacitor. You know that the impedance of a capacitor is 1 upon SC. So in this case, the impedance of the capacitor is 1 upon SC1. And since S is equal to J omega, at DC, omega is 0. So 1 upon J omega is infinitely large. So the impedance of the capacitor is infinitely large on the left side. The impedance looking into the op amp is infinitely large looking on the right side. So current can only go from top to bottom. And that means even though there are 4 components connected at this point, you have RB1, RB2, C1, and the op amp connected at this point, current only flows between RB1 and RB2. Current does not go, or the DC current does not go in other places. Okay. So that's the reason why the voltage at this point is going to be VCC over 2. Now that is exactly half of your maximum voltage and minimum voltage. That's exactly what you wanted to have as biasing point for your op amp. So RB1 and RB2 and the subscript B stands for biasing in this case. So these are biasing resistors which are making sure that the input DC point of your op amp input is 5 volts. Now, why do you have this capacitor? In that case, you may argue that what's the need of this capacitor? The need of this capacitor is you want to apply or you want to have a 5 volt at this point, right? But the voltage source over here, let's say that's an AC voltage source, but that can also have a DC voltage. Let's say it has a 0 DC voltage of 2 or DC voltage of 0 volt or DC voltage of 100 volts. We don't know. So we don't want the DC voltage of the source to affect the DC potential at the midpoint of RB1 and RB2. So you want to isolate the DC of this part with the DC of whatever the op amp is seeing. And the capacitor, because the capacitor offers infinite impedance at DC, it can isolate 2 DC voltages because there will be no interaction between those 2 DC voltages as there is no DC current flow through a capacitor. So the capacitor is isolating the 2 DC domains on the left side and right side. But it couples the AC because, again, you know that the impedance of the capacitor is 1 upon SC. So for a sufficiently large frequency, if the frequency is sufficiently large so that 1 upon SC is sufficiently small, you can assume your capacitor's impedance to be a short. And yeah, imagine infinite frequency. At infinite frequency, S is infinite, so 1 upon SC is 0. So the capacitor's impedance is 0 in infinite frequency anyway. But let's say at a sufficiently high frequency, your capacitor's impedance is sufficiently low, which means that you have almost a 0 impedance or a 0 resistance for AC. But for DC, you always have an infinite resistance. So that's the job of your C1 capacitor. What's the job of your C3 capacitor? That's also doing the same thing. It's isolating whatever is happening at the output end with the DC potential of the op amp's output. So you want the op amp to be in a bubble. You want the op amp to be in a bubble, and that bubble around this op amp where you can control what your DC potentials are going to be. And if you can control what your DC potentials are going to be, you have a very good control over your gain. And that's what you want to achieve for your op amp. And that's the reason why you put these DC blocking capacitors at the input side and output side. They are sometimes called DC blocking capacitors. Sometimes they are called coupling capacitors. Why coupling capacitor? Because they couple the AC. They couple the AC but block the DC. So you can call them the DC blocking caps. You can also call them coupling caps. All right. You have another capacitor over here, which is interesting at this point. And we'll actually discuss what kind of effect this capacitor has later on. But then again, what you might say is that for AC, what you are doing over here is that for AC, this capacitor is a short, which means that you have a shorted path to ground for any kind of AC signal. And that means you have this R2, which is 40 kilo ohm, divided by R1, which is 1 kilo ohm, as your gain, or basically the factor that determines the gain. That's the R2 over R1 factor. And because in this case, you're applying your input to the non-inverting terminal, you have 1 plus R2 over R1 as your gain. But remember that for that AC gain, the capacitor C2 has to be shorted. So the frequency at which you are operating has to be sufficiently large so that the capacitor C2 can be sufficiently small impedance. But in terms of DC, you will have no DC path to ground. You do not have any DC path to ground. What that means is the DC voltage at the output, let's say at this point, and the DC voltage at this point will be exactly the same. So let me clear this out to make this point a little better. That what is the DC voltage at this point if you do not have this capacitor? Right? If you do not have this capacitor and let's say the bottom terminal of the R1 resistance is directly connected to ground. In that case, there is a DC potential here. There could also be a DC potential here. The DC potential of this point will be 0 because it is connected to ground. But because there are always current flows, it's not very clear, like immediately, that what's going to be the DC potential at this point. But you want the DC potential of that to be a certain value. And what do you want that DC potential to be? Because there is a virtual ground property, you also want a 0 difference between the positive and the negative terminal of the op-amp. So if this point is 5 volts, the positive terminal, the negative terminal, you also want that to be equal to 5 volts. Now, because this is directly connected to ground, you will have a DC current flow from here to ground. And that DC current flow is something that will mess up, or eventually you'll see that if you do a lot more analysis, you'll see that that DC current flow does not help you in any way, but it can mess up certain voltages and currents. So if you want to avoid that, you can just put this DC blocking capacitor here that will stop any kind of current going from this point to ground. And what that will also do is that the DC potential at this point, which is 5 volt, because now there is no DC path going to ground, the entire DC current has to go through this resistance and at the input side of the op-amp. So which means that the DC potential at the output of the op-amp is also fixed at 5 volt. Now you have both the inputs fixed at 5 volt, which is at the middle of your VTC curve, and your output is also fixed at DC 5 volt, which is at the middle of your VTC curve. Okay. So you can fix your output and input DC points just by having this additional C2 capacitor, which blocks the DC going from your V minus to 0. Okay. So in terms of AC, whenever you need to do any kind of AC analysis, ignore what has been done for DC. So what has been done for DC in this case? Of course, you have these DC blocking capacitors. For AC, this capacitor will be shorted. So you have a shorted capacitors. These are just creating the DC biasing point. So these are also not important for your AC analysis. So you can get rid of them. This capacitor over here, that also becomes a short for your AC analysis. So just make it a short. This capacitor over here becomes a short for your AC analysis. So now you see your circuit is simplified, right? This capacitor is gone. all the three capacitors are gone, and this RB1 and RB2 resistors are gone. So when you're trying to find out what is the AC gain, now you have a very simplified version of the circuit because other components were related to DC, but they were important because you anyway want to have a DC point set up first, the biasing point set up first, before you can actually expect AC gain. So, okay, now with that, I think you should be able to go through or understand how this problem is solved. Okay. Oh, okay. So one small thing that I want to mention. So for this part, where you are asked to find out, asked to choose values for C1, C2, and C3. You want to choose values for C1 and C2 and C3 to set the lower -3 dB frequency to 50 Hertz. And assume FL equal to 50 Hertz for the rest of the problem. So you want to set a frequency, some sort of a frequency limit, the lower -3 dB frequency. Let's understand what is meant by that. Now, for this particular circuit, consider the effect of all these capacitors. So for example, let's just take this capacitor for a moment. This capacitor and this resistor on the right-hand side, let's just consider that first. So these two, they create a high-pass filter, right? Because you have a capacitor in the series path, and then you have a resistor connected to ground. Why is this a high-pass filter? Because unless the capacitor is shorted, there would be no signal coming from the left side of the capacitor. So the capacitor has to be shorted for any kind of voltage to be available on the right side of the capacitor, which means you need to have a relatively high frequency. And that's why a series capacitor connected to a resistor to ground is a high-pass filter. Similarly, in this case also, the current was the signal was coming from left. You have a series capacitor, and on this side, looking on the right side of the series capacitor, what do you have in terms of AC? In terms of AC, you have this RB2 resistance going to ground, and you have the RB1 resistance going to VDD, which is also AC ground. So even your supply is an AC ground, right? So looking into the right side of the capacitor C1, you see RB1 in parallel to RB2 when you are doing AC analysis. So remember that now the RB1 and RB2 were there to do DC or to make sure that you have a DC biasing point. But just because they are there for the DC biasing and they do not impact in the gain, that you're interested in, but they will impact in the bandwidth. How would they impact in the bandwidth? Because there is a capacitor and there is a combination of resistor looking on the right-hand side of it. So they will create this high-pass sort of a filter. And the high-pass filter's cutoff frequency would be related to 1 upon RC, where you are interested in the capacitor and the resistor associated with it. Okay. Now the way to analyze this, you now see that C1 creates a high-pass filter, C3 creates a high-pass filter, C2 interestingly also creates a high-pass filter. Why does it create a high-pass filter? Because what happens at low frequencies? What happens at very low frequencies is that this capacitor C2 is open. So at DC, the capacitor C2 is open. And if the capacitor C2 is open, then the bottom terminal of R1 is kind of hanging. And unless the bottom terminals of R1 is connected to ground, you do not have the circuit for your non-inverting amplifier. Remember, how does the circuit of the non-inverting amplifier look like? That you have an input connected to the non-inverting terminal of the op-amp, but there is a resistance R2 connected from the output of the op-amp back to the inverting terminal, and there is a resistance connected from this point to the ground. That has to be there. Unless that is there, it's not a non-inverting amplifier. So for the non-inverting amplifier to exist, the frequency has to be high enough, because unless the frequency is high enough, C2 is not a short. So this is also a high-pass filter because it only allows higher frequencies to pass through the system. So all three of them, C1, C2, and C3, creates some kind of an high-pass filtered pole, right? 1 upon RC. The way you analyze this is look at each of the capacitors one by one. So for example, first look at C1. So first try to consider, this is called open circuit time constant method, that you try to find out the time constants related to or to each of these capacitors, and you consider each of the capacitors one at a time, and you assume the other capacitors are not present at that point, because again, you don't want to make your life too complex when you're doing hand calculations. This gives relatively accurate results, but of course it's not exact result that you'll find in a simulation. But with relative amount of accuracy, good relative amount of accuracy, you will find out that if you just consider C1, C1 will see what? See on the right hand side. So let me just see one separately. So this is C1. And looking on the right hand side, you will see RB1 in parallel with RB2. So RB1 in parallel with RB2. Why we're saying that these two are in parallel? Because in terms of AC, RB1 and RB2 both are in parallel, because the other terminal for both is AC ground or virtual ground. This is actual ground. The top terminal of RB1 is virtual ground, because any VCC is virtual ground. So RB1 in parallel with RB2, that's what you have on the left side or right side. On the left side, you have RS. So you're basically trying to find out what is the Thevenin equivalent resistance present between the two terminals of this capacitor. The Thevenin equivalent resistance present between the two terminals of the capacitor is this, because you already need to get rid of this source voltage. So you have RS on the left side and RB1 in parallel, RB2 on the right side. So what is the overall Thevenin voltage if you traverse this entire path? You have RS plus RB1 in parallel with RB2. So that's basically 501 kilo ohm if you just put in the values. C2 will only see this R1. Why? Why would it only see R1? Because this point is virtual ground. If this is virtual ground, the negative terminal is also forced to virtual ground. Again, remember that this is not actual ground, but in terms of AC analysis, you're forcing this point to virtual ground. If that is virtual ground, C2 will only going to see R1. So just do an RIN calculation at this point, right? So if you do an RIN calculation at this point, it will be equal to R1. And C2 will only see R1, which is equal to 1 kilo ohm. And C3 is going to see, in this direction, it is going to see RL or whatever it is, this one, 50 kilo ohm. And in this direction, because you are seeing the op-amp's output, you're going to see 0. So for C3, if I draw the same circuit as I had drawn earlier, so this is C3. There is some amount of resistance on the right side, and the left side you have 0. So what is the total resistance that you see for C3? You're seeing this R3 resistance, which is 50 kilo ohm. So you have all the three resistors or all the three equivalent resistances corresponding to C1, C2, and C3. So 1 upon RC for all these three conditions you can figure out. If your lower minus 3 dB frequency, or basically the 3 dB pole that you want to have at 50 Hertz, you can select any of these capacitors to be at that 50 Hertz. But we already discussed in the previous class that it's important to have a first order system whenever you're dealing with op-amps. So you should not have all the three poles on the same location. So you should have a 50 Hertz, then you should have a minus 20 dB per decade or minus 20 dB per negative decade, basically, because this is a high pass filter, as you're reducing the frequency by 10 times, you are reducing the gain by 10 times as well. So you should have that minus 20 dB kind of slope. And for that, you need to have a first order system. So the second pole and the third pole has to be significantly away from the first pole. So you select any of the capacitors. Let's say, for example, in this case, you're selecting, let's say, C2 creates that first order, this pole, the first pole. In that case, you can find out the value of C2, because C2 is seeing R1 equal to 1 kilo ohm, and then 1 upon 2 pi RC is equal to your frequency, or C is equal to 1 upon 2 pi F times R. So you can put all those values together and you can find out what is going to be your C2. Now C1 and C3, for them, you want to choose the pole in a way that the pole is at least 10 times away from the dominant pole over here. So this is sometimes called the dominant pole. So you want to have the other two poles at least 10 times away so that their effect is not that much. So you choose your C1 and C3 in a way that, oops, let me clear this. You choose your C1 and C3 in a way that these are 10 times away. The frequency is 10 times away. So this is actually at 5 hertz. So 50 hertz divided by 10 is 5 hertz. This is 50 hertz divided by 10 is 5 hertz. So choose those at least 10 times away from the dominant pole, and that would give you the value of your C1 and C3. Now you could have chosen any other capacitor to have the dominant one. So you can choose any one of them to create the dominant pole, and the other two should be the non-dominant poles, which should be 10 times away from the dominant pole. So let's stop here. We'll start from this point on Wednesday's lecture. But this is very important to understand how those poles affect your overall frequency response. All right, I see there was a question that why doesn't C3 see R2? But I think you already figured it out why C3 does not see R2. Okay. There was another question on the biasing point setup. Maybe we can, I'll stay back on the call because this is also office hours. So maybe if you have any questions, please stay back. We can discuss them in the office hours. Okay, let me stop the recording.